Hey everyone. We're really excited to have Nicholas Baca, co-founder of Ledger and innovation lead. He'll be doing a talk around modern Bitcoin transaction signing on a smart card chip. And I'll let him take it from here. Can you guys confirm in the chat that you can hear us?
Hey, hi everybody. So thanks for hosting me. I'm waiting for the confirmation, I guess, or is it fine?
Yeah, it's fine.
Okay, that's fine. So I will go ahead. So today I'm going to talk about Bitcoin signature on smart cards because I think smart cards are a great tool for resilience, which is often overlooked. So I will try to make a small overview about what smart cards are and how they can help making Bitcoin signatures more resilient. So, small overview of that talk. So I will start by talking about smart card chips, explaining exactly what they are and why it's interesting to look at them. Then an overview about Bitcoin signature and more specifically Bitcoin multisignature, because it's great to mix devices when you want to secure your Bitcoins. I will go through issues that you can have today with Bitcoin multisignature on when using hardware wallets and different signing devices, and finally talk about a few improvements. So that's going to be very practical. I'm not going to talk about Schnorr or about Taproot. I'm really going to be down to earth regarding the problems that we have today and how we can solve them in the coming months, let's say. So first, a small overview about smart cards. So I think it's important to mention all the differences that you have between smart cards and MCUs, because today situation is a bit confused sometimes. I mean, you hear about secure elements, but well, it's not very clear if you are talking about accelerators or smart cards or something else. So about smart cards, first, important thing is the CPU. If you compare a smart card chip to an MCU, you will see that they are running more or less the same chip, so they are running on ARM. The difference with a smart card is that the ARM core is hardened against physical attacks. So if you are an attacker and you want to glitch the card or you want to extract data from a smart card, it's going to be extremely difficult by design. So that's one thing. Then the speed. Things start getting a little bit more interesting for developers over there, because you see that an MCU is pretty fast. I mean, well, fast as an embedded computer can be, but smart card is 10 times slower often. So the crypto processing is fast enough, I would say, but everything else is pretty slow. The development tool chain is pretty non-standard as well. I mean, on most cards today, you are going to have to rely on a mix of Java card and global platform. So Java card is not really close to Java. It's more like if you were writing assembly with a Java sugar and Java bytecodes, but in the end, you're not going to do some fancy object-oriented programming. So it's very low level. The Flash is not too interesting. I would say today they can completely be compared. The RAM gets here more interesting for developers because you see that you have very strong constraints. If you want to work on a smart card chip, you have 10 kilobytes is pretty common, 50 kilobytes is what you get. And if you get a really top of the line smart card, so not the kind of card that you have easily, while MCUs are enjoying a very large RAM amount compared to that. So I would say at least twice, but often more. And the price gets here quite interesting as well, because smart cards are extremely cheap. And that's why I think they are interesting to make Bitcoin more popular and signature more popular, because when you scale, you can get a smart card for a few tens of cents. Often with radio, so with NFC, while if you want to scale on an MCU, you can't really get below $1 because you have a lot of extra logic that is impossible to strip, let's say. Then looking at the device deployment strategies between a smart card and what I would call a composite device, so a device that would mix an MCU and some kind of secure element, things are completely different regarding the way you are going to load code. So it all starts at the factory. At the factory on a smart card chip, the manufacturer is going to load a bootloader that will let you load the code at the issuer stage. So when you are the issuer, you are loading code that is completely protected by the manufacturer, and that's not something that you can do when you are loading code on an MCU, because when you are operating on a mix between an MCU and a secure element, the only thing that is set at factory is secrets on the secure element, but the bootloader of the MCU is something that you put yourself, so it's not something that would be enforced by the manufacturer of the secure element. So to summarize, the biggest difference you have between deploying code on a smart card chip and deploying code on a composite device made of an MCU and a secure element is that you will have a domain split between the logic and the secrets. So on a smart card, you have the logic and the secret on the same chip. So if you want to prove something, you can prove with one very simple statement that you are running the right code with the right secret on the right platform. If you're running on a composite device, things get a bit more complex because you have to make sure that the link between the MCU that won't be protected and the secure element that is protected is still secure. So that's an additional security problem. So here you have a way, when you use a smart card, to demonstrate to an external observer that you are running on a genuine platform very easily. To summarize the pros and cons of smart card chips, and well, as I am very non-biased, you'll see I have 4 pros and 3 cons. So on the cons, well, you don't really have standard development environment, so you have a lot of Java card things, a lack of native SDKs. I would say at Ledger, we are pushing for more native development on smart cards, but we are pretty much the only player to do that today. So you have a lack of manufacturers. You can find a few, so you have Gemalto, Giesecke, and so on. But you don't have many, I mean, compared to manufacturers of other embedded chips. And so you have that issue with low RAM and performance, but we'll see how that can be overcome and what really the issue is. So on the pros, they are designed to be protected against physical attacks. That's really the strongest part. You get a free validation of the platform with everything in the same security boundary. The price is very low, so that's great if you want to scale. And I put that as a pro, well, as I said, because I am very non-biased. You are forced to optimize your software. And that's great because if you develop something that can fit on a smart card, you're pretty sure that it can fit anywhere else with better performance. So that's a good way to look at the problem from a developer point of view, in my opinion. So quick summary of how a Bitcoin transaction is signed on a hardware wallet. So for people who are not familiar with that, the problem from a very high level is basically, well, like that. So you have the host. The host is considered to be insecure. The host is going to have UTXOs that you want to sign, the key path of your hierarchical deterministic keys that you want to sign with, the output. So everything that forms the transaction, you are going to give that to your hardware device, so to your hardware signing device, using a proprietary protocol usually. So it can be any kind of transport. I mean, it can be USB, BLE. You have some devices supporting SD cards or QR codes, but well, the protocol is proprietary usually. The device is going through the different elements that have to be signed, is providing you with some information about what is getting signed, and is returning the signature without exposing the keys. So that's basically how hardware wallet works and how smart card would work in that logic. So the great thing is that recently all those parts have been standardized at a high level. So the data you have to provide to the card has been standardized as part of the partially signed Bitcoin transaction BIP, so which is BIP 174. And the protocol adaptation has been done for several hardware wallets, so for Ledger, for Trezor, for Coldcard, with a project in Python called Bitcoin Hardware Wallet Interface. So that's great because it means that all that logic that was before very proprietary has started to be standardized. You still have a couple problems, I mean, on all hardware wallets and on all smart card logic that you would like to develop when you are signing a Bitcoin transaction. So the first problem is the run size, because even when you are not a smart card, you are going to have to process a transaction. So transactions can be pretty big. I mean, if you have a transaction that is 1 megabyte in size and you have only 128 kilobytes RAM, you have to be a little bit creative, I would say, when you pass it. So for most devices, transactions have to be streamed to the device. So we have to cut your transaction in smaller parts, put it to the device, and then process it on the fly. And PSBT is primarily designed for, I would say, not being passed, because it's a large blob of data. So it works better if you can use it as mass storage. Otherwise, you have to go through the adaptation that I was talking about. Then regarding the performance, signing data processing is pretty complex. So it got less complex with SegWit, because before SegWit you had to hash all the inputs. I mean, as many times as you had inputs in your transactions. So SegWit reduced that, but it's still a lot of work. I mean, for something that's not necessarily very fast, especially if it's a smart card. And the biggest problem that, there was some exploit that was documented recently about that, but developers have been aware of it for quite some time, is that SegWit doesn't commit you on the full set of UTXO values. So, which means that if you have a commitment per value of each UTXOs in SegWit, but if you want to get a proper value for the fees, so if you want to basically get the right information about what is going to be sent, you have to create that commitment yourself. So you have to process all the previous UTXOs in the device, which means hashing the transaction again, which means, well, additional work and additional slowness, for the whole process. Now, going beyond just Bitcoin signature, if we want to look at multi-signature, because that's what people usually use those devices for. If we look at the most boring form of Bitcoin multi-signature, well, an MFN multi-signature, we have one opcode, we have multiple keys, and that's it. So that's still, something that is, well, pretty simple when you look at it, but we'll see that we have some problems. So some are pretty easy and some are, well, not that obvious. So the first completely obvious issue is that you have to identify the public keys before doing a multi-signature. So that's absolutely obvious, but it's just good to remind people about that, because if you are signing, you are going to sign over a different set of keys, and you have to establish an off-process channel in order to exchange those keys and verify that the keys are the right keys, because otherwise, if you are just signing addresses, well, somebody could replace a key as a man in the middle, and then you would be signing something that you couldn't spend, or worse, you could be signing stuff for someone else. So you don't want that to happen. But that issue is pretty obvious. We'll see that the second one, which correlates in this one, is pretty obvious as well, is that you want to validate your multi-signature agreement. So when you are signing device, you want to verify, for example, that you are signing for the right quorum, so that you are really signing for 2 of 3 and not for 1 of 2, which means that you have to be able to have some ways to validate the script. Because if you can't validate the script, if you are just looking at the address, you don't really know what the script is. So you have to be able to do that. So you see that even if it's obvious, it gets more complex if you are limited in processing power and RAM size. Now, going to an issue which is a little bit less obvious, I would say, is that you have still to validate your multi-signature agreement, but in Flux. So in Flux, when you are consuming the transaction, when you are consuming an input and you are sending funds to some other party, you are going to get back a change amount. And this change amount is going to be sent on a change address, and this change address should match the actual agreement that you had in your multi-signature. Otherwise, you can lose funds that way. And the device should detect that automatically and should not prompt you to validate it, because otherwise the UX is going to be pretty confusing. So the problem with this is that you have a lot of things that define what a transaction should look like when you are handling those change outputs, but it's pretty much a lot of duct tape that's put together. So you have BIP45 that will define a set of paths that you can use to do that. You have BIP67 that will define how the public key should be sorted so that everybody agrees. And you have PSBT itself, which says that, well, to know what is a change output, you should basically pass the input, and I'm just quoting the sentence, the bold sentence, so it should determine the general pattern of the script and internally produce a representation of the policy that the script represents. That's not super clear. And especially when you don't really have enough memory to parse the script, or when you can't know what the script is, because let's say you are signing a SegWit transaction, you don't see the witness as the signer, so that's a lot of, that's a bit messy. But still there are ways to do that correctly in a simple multi-signature process. If you assume a lot of things, you can pretty much get that right. But let's say that you don't assume a lot of things, and you want to do modern Bitcoin multi-signature. So that's it. You don't just want to do multi-signature. You want to use some scripting logic. And for example, you want to say that you have a multi-signature with A and B that are live, or C and D that are offline. And you want to switch between both set of keys. So that's something that's very easy to do with Bitcoin script. But here, the auto-probing of PSBT is not going to tell you what the change what the change output is going to be like. So if you want to validate that automatically, you have to be a little bit more creative. And The other thing is that, well, if you want to have a change policies that varying over time, I mean, let's say, for example, you want to lock a transaction for some duration for the first change and for a different duration for the other change, still that's something, I mean, where you are missing something if you want to do that properly in your signing device, and if you want to provide the right information to the user, which is a key part of those devices. I mean, you should not be validating things blindly, basically. So the very good news is that everything, I mean, all those problems have already been solved. So they have been solved with a set of different protocols. So the problem of first producing a human readable script has been resolved by Miniscript, so which was done by SIPA some years ago, I think. So it's not very popular, but it's going to be more popular, I mean, now that it's integrated in a few wallets. And recently, you had some things that built on top of Miniscript to create an even easier representation of the script, so-called Minsk, which is, well, super interesting as well. I have some screenshots that you can't read over there, but I will suggest to see the URL for yourself, and it's pretty nicely done. And the other problem that we have when validating multi-signature on a signing device, which is to validate, I mean, how the keys are going to be derived for the different in Flux, so for the different change that is addresses that are going to be produced, has been resolved by descriptors, so which are another specification which has been recently implemented in Bitcoin Core. And wallets are starting to use that. For example, you have a wallet called Magical Bitcoin that extended the descriptor to use to support variable derivation paths, so which is exactly what you need, I mean, when you want to do that kind of control and that kind of policy checks. So we have something that looks very nice on a diagram, and we would really like to be able to do that. So we basically run through a set of stage on our hardware. When the host is holding the Miniscript policy, it's going to send it to the hardware wallet. And the hardware wallet can give you some description of the policy, can display the policy to you. So you can be offline, for example. You are going to check your policy when you receive your PSBT. Well, you could also generate a policy directly from script in PSBT, because it works in both ways. But let's say you compose your policy, you send it to the wallet, you are convinced that the policy is correct, the wallet is returning you a signed policy so that it can commit. And then in a second stage, when you are going to sign your transaction, you would start by sending your signed policy to the device along with parameters. So parameters would be at the bare minimum, the index of the keys that you are going to derive, and other things, I mean, to be able to format the script properly. And then you go back to your old PSBT signing logic. So you don't change anything. You don't have to change anything in PSBT. You just have an extra commitment that's going to be done by the signing device on the Miniscript policy that has been, well, sent right before the signature. And if the policy matches, then everything is fine. If the policy doesn't match, then the device is going to reject the operation. So it looks very nice. But now if we look at, well, how could that be done in real life? So in real life, if we go through the different stages of Miniscript, so first, you can express your Miniscript policy in a high-level language, such as Minsk. So that's not something you are going to do on device, because the logic is complex and it's pretty much RAM-intensive. Then Miniscript policies themselves are compiled, I mean, into Miniscript. So Miniscript policies are much more readable than Miniscript itself, but here, doing the compilation stage, I mean, in hardware, it's probably doable in a generic, in a high-level hardware, it's probably doable. On the Smartcard, it's definitely non-doable because it would be too RAM-intensive. But if you just focus on Miniscript, so the part that is right before the conversion to Bitcoin script, then it's simple enough. And, well, I'm pretty sure it can fit. I mean, I already did a few tries, so I will keep doing those tries. That's a general idea. But I think here we have something very interesting to be able to commit to what we sign exactly, even for complex transactions. So the device guarantees here would be to give you a way to review Miniscript, so not the policy itself, because it's probably a bit too resource consuming, in human readable form. So if you have a display, or if you don't have a display, you could send a hash of the policy that you are going to commit to another device, validate that hash, and the end user would be able to verify that on an offline computer, or well, how this could be integrated into PSBT as an extra option that you don't need, but that you would support if you have that kind of signing device. Then you lock on the script production, and you have additional guarantees starting from there. So where are we going next? Because we are already at the end of that presentation. So I'm going to work on a more detailed description of what this thing that I am calling detached miniscript can look like. So how can we basically strip the last part of miniscript to send it to a signing device with very low RAM, and how it could work to improve Bitcoin signing. I'm going to do that on the next version of the Ledger Bitcoin application, which is open source. So since it's open source, that's something that could be adapted to other smart card chips. And typically, I would invite people to play with Java Card and see how this can be done, and how we could have multi-signature devices that, well, are just more trustable in the future. I will be probably tweeting about that. So the best way to follow progress on that is to follow me at BTChip. I'm not tweeting a lot. I'm not fighting with anybody, and I'm not tweeting in French, so I'm not going to harm you. So thanks for listening, and that's for this short presentation of today. And I guess I'm going to the questions now. So I'm getting the question in the chat, right? Or no? Oh, yeah. So is Ledger going to incorporate smart card chips into the Nano S and the Nano X? So Ledger is based on smart card chips. So we already have a smart card chip in the S and in the X. So smart card chip is an ST31 in the S and an ST33 in the X. We are running on our own operating system, which is called Bolos. The main difference between that and other Java Card platform, I would say, is that we allow for native programming on the smart card chip. So today we provide you with the ability to use one of the most secure device that is available on the market and run native code on top of it. So that's something that everybody can do on the S, and we are working on getting everybody to be able to do it on the X. So that's pretty much done. And then hardware wallet are pretty complicated for non-savvy tech users. So what are your thoughts on possible ways to promote user adoption? On the short term, I think we have a lot to do on the user experience. So probably, we can think about some processes where, the way you store your mnemonic, for example, is different, is easier. There have been things done by blockchain commons, for example, to think about new way to store mnemonics, so with words that rhyme, or with other mechanisms. Because I think here's the balance that we want to hit, and that's quite complex to maintain. Is that we want to be easy to use, but we want to be interoperable and completely non-custodial as well. So usually, when you get easier to use, you get less less self-custodial or less interoperable. For example, if you consider that it would be nice to have one third party storing one part of your mnemonic, that would make user experience much easier for sure. But then, if the manufacturer disappears, or if you lose, your relationship with this party which is holding part of your mnemonic, you can't recover, which is a shame. So on that, we are pretty much looking at what could be done to make that easier, while keeping in mind that you still want to be non-custodial. So we are thinking about user experiences improvements, let's say, and that's basically our focus. So we are doing that with Ledger Live. We are doing that with different experiments. Maybe another application that could be easier. Maybe something that's partnering with other people that promote solutions that are easier to use. So we are pretty open to solutions to make the user experience easier. So does Ledger use multisig? So the device itself supports multisig. If you look at it's integrated with HW, so with the hardware wallet interface, HWI. So you can't today do a multisig with Ledger Live. That's something that will be on the roadmap, for later. But you can do a multisig with Ledger and Electrum, for example, multiple other software. There have been plenty of new software supporting multisig. So I'm thinking of Spectre right now. I think there has been one announced a few days ago called Lily, if I remember well. So that's something that's getting popular. So you can definitely use a Ledger device in a multisig setup. It will have some drawbacks today, so it won't display, for example, as many information as other devices because it has less power and because, I put the focus, on multi-signature validation and flexibility rather than supporting hard-coded script formats. So today we validate a bit less than other people, but the idea is that with that kind of specification and with Miniscript friendly to use with other hardware wallets, everybody would be able to do much better validation than what is being done today. So that's what I am hoping in the future. But so for the short answer to the question, yeah, you can use multisig, just not with Ledger Live. What do you think of the swipe tech? So I don't know what is the swipe tech. If we are talking about the old magnetic swipe technology, but I guess that's probably not the question. So if you can elaborate on the chat, what do you mean about swipe? I would be happy to answer. Then why not make the key able to be open used with fingerprint or facial recognition? So here, as we want to be an independent device, I think the only thing that would be applicable would be biometrics, so using fingerprints. I'm not a big fan of fingerprints today because, that's a technology that's first based on statistics. So you don't really know, what makes your fingerprint recognized on the device. So you have a lot of secret sauce in everything, in the sensor, in the matcher, in the way your fingerprints are digitalized in the first place. So you put a lot of trust into something that you don't really control. So that's the main reason why we are not using that. And I would say that fingerprints are probably nice as well to unlock a device once it's already unlocked. But you don't want to put all your entropy in a fingerprint. So I would say that today, between a pin that you're going to enter on your device manually and a fingerprint, when you power up the device, I would be much more comfortable with a pin than with a fingerprint. After the device is locked, using a fingerprint is kind of okay. But on platforms that are much more complex than ours, because if we wanted to use a fingerprint reader on a smart card, I'm thinking about smart card with integrated fingerprint there, but if we wanted to use a fingerprint reader with Ledger, we would have to go for something that's very low cost. And if you take a fingerprint reader that's not very well protected, I would say you definitely put your user at risk because then it's trivial to forge fingerprints and it's trivial to recover your fingerprints from any space. For example, if you touch your phone, you could recover the fingerprint, so that's not. So, that's the reason why we are not very, very keen on using that. So Swipe is making a wallet with a credit card and, okay, that's Swipe. Okay, sorry. So all those people, as far as I know, they are basically doing cards, top-up cards, so that you can top up with any kind of cryptocurrency, and then you can use those cards, to pay for regular expenses because they are inside their EMV cards. So they are standard credit cards that you can top up with cryptocurrency. So that's the thing. They are not really used, as far as I know, to sign transactions. But when they are used to sign transactions, they are on the Ethereum blockchain. So Status is doing one, which is open source as well. So it's nice to look at. I would say that signing Ethereum transaction is much, much easier than signing Bitcoin transactions because you have a constant time when you want to sign an Ethereum transaction because it's not UTXO based, so you know that you just have to sign a hash, while signing a Bitcoin transaction can definitely vary, depending on the number of UTXOs that you have. So if you want to do a thing that is pretty generic, And if you want to be interoperable, signing a Bitcoin transaction over NFC is pretty complex.
Awesome. Yeah, this was a really great presentation. Thanks so much for taking the time.
Thank you.
All right, we're going to transition to our next talk now. Thanks.
Bye-bye.